High-pressure die casting, or HPDC, forces molten aluminum into a steel die at extreme velocities, applying pressures that reach up to 2,000 bar. Immediately following this violent injection, the molten metal meets its secondary constraint, a massive thermal drop. The cold steel die triggers a near-instantaneous cooling cycle, freezing the liquid aluminum in milliseconds. At a macroscopic level, this rapid process yields clear manufacturing benefits. It allows for high production rates, the creation of complex part geometries, and a smooth surface finish. However, those outward benefits mask a complex internal reality. The speed of the cooling process creates extreme thermal gradients, resulting in a chaotic, highly stressed microscopic architecture inside the metal. The mechanical integrity of an HPDC component, whether it holds pressure or shatters under load, is dictated by this non-equilibrium microscopic architecture, rather than its bulk exterior shape. To understand a casting's strength, we look inside at its microstructure, a dense landscape of distinct grains, phases, and voids. This chaotic arrangement results from non-equilibrium solidification. Rapid cooling locks chemical phases into place before they can organize. This thermal imbalance creates a skin versus core division. The outer metal cools fastest, forming a dense, fine-grained skin, while the center cools slower, resulting in a coarser core structure. Controlling the quality of the final part requires engineers to precisely map and manipulate this exact distribution of microscopic phases. Mastering high-pressure die casting means treating the process as a rapid-fire chemical environment, where severe temperature gradients dictate the physical survival of the component. If we reset the model to a purely liquid state, the first phase to emerge during cooling is the nucleation of the alpha aluminum phase. Alpha aluminum grows into microscopic, branching tree-like structures called dendrites. If we zoom into a single dendrite, the atoms are arranged in a face-centered cubic, or FCC, crystal structure, a symmetrical lattice with an atom at each corner and the center of every face. This specific FCC geometry provides the alpha aluminum phase with high ductility. The atomic planes can slide past one another under stress, allowing the metal to bend rather than snap. Because of the aggressive cooling rates in HPDC, these alpha aluminum dendrites remain exceptionally small. This fine grain size mathematically boosts the overall strength of the part compared to slower methods like traditional gravity casting. The dendritic matrix forms a flexible, load-bearing skeleton. This ductility allows an engine block to slightly deform under thermal expansion rather than fracturing. As the alpha aluminum dendrites solidify, pockets of liquid metal remain trapped between the branches. To reinforce these gaps, HPDC alloys rely on a critical secondary element, silicon. This remaining liquid undergoes a eutectic reaction. This is a process where a single liquid simultaneously crystallizes into two distinct solid phases, in this case, a finely mixed dual-phase structure of aluminum and silicon. Eutectic silicon delivers a massive increase in localized hardness. When subjected to friction, the rigid silicon particles protect the softer aluminum dendrites, increasing the part's overall surface wear resistance. However, this creates a strict metallurgical trade-off. While silicon is incredibly hard, it is also inherently brittle. If the alloy is oversaturated with silicon, the entire component becomes fragile. Silicon is the indispensable armor of the alloy matrix, but if improperly balanced, it becomes the exact mechanism for fatal brittle fracture. To push mechanical limits further, tertiary elements like copper and magnesium drive precipitation hardening. This is a mechanism where tiny, hard particles form within the metal matrix to impede atomic movement. These elements form microscopic phases, specifically aluminum-copper and magnesium silicide. These hard precipitates lock into the boundaries between the dendrites and the eutectic filler, restricting microscopic movement and raising the part's overall tensile strength. This chart shows the compromises introduced by copper. As the copper concentration increases along the bottom axis, the tensile strength line rises sharply, while the line representing corrosion resistance plummets. High copper concentrations also introduce a secondary physical threat. The element increases the alloy's vulnerability to hot cracking, microscopic tearing that occurs during the final stages of solidification. Adding strengtheners to the melt is a zero-sum engineering calculation. Increasing the raw load capacity of the casting inevitably sacrifices its environmental durability and castability. Unlike copper or magnesium, iron is technically an impurity, yet a specific amount of iron is deliberately tolerated because it chemically prevents the molten aluminum from soldering to the steel die during injection. Left uncontrolled, iron adopts a disastrous physical morphology, the beta iron phase. It crystallizes into sharp, invasive, needle-like plates that pierce directly through the ductile alpha aluminum matrix. These rigid plates act as extreme stress concentrators. When mechanical load is applied, the force multiplies at the sharp tip of the beta iron face, initiating a jagged microcrack that compromises the entire structure. To neutralize this threat, metallurgists employ a precise chemical countermeasure, the addition of manganese. Manganese atoms bond with the iron, triggering a morphological transformation. This forces the iron out of its sharp beta plate form and into an alpha iron phase, a rounded geometry often called Chinese script. Because the sharp edges are eliminated, mechanical stress dissipates harmlessly. Advanced metallurgy requires utilizing specific chemical additions to morphologically disarm the physical threats of required impurities. The final non-solid element of the HPDC microstructure is porosity, the physical presence of empty voids within the metal. Porosity forms via two distinct mechanisms. Gas porosity occurs when air or dye lubricant is trapped in the metal, forming isolated spherical bubbles. Shrinkage porosity occurs when the metal contracts as it cools, tearing open jagged, interconnected cavities between the dendrites. Shrinkage porosity is particularly destructive for pressure-critical parts. Because these jagged voids are interconnected, they create direct, continuous pathways for pressurized fluids to leak through the solid cast wall. Even microscopic gas porosity drastically reduces a component's fatigue life, the number of stress cycles it can endure before failing. Under repeated loading, every microscopic bubble acts as a weak point waiting to rupture. A perfectly engineered phase matrix is functionally useless if interconnected porosity severs its macroscopic continuity. Because alloy chemistry alone cannot solve all structural defects, foundries rely on active manufacturing process controls to enforce this phase balance on the factory floor. To prevent silicone from becoming too coarse, chemical modifying agents like strontium or sodium are injected into the melt. These agents artificially refine the eutectic silicon, keeping the particles microscopic and evenly distributed. To combat gas porosity before the metal reaches the die, operators use rotary degassing. This mechanical process spins a rotor inside the liquid aluminum to extract dissolved hydrogen gas, preventing it from forming bubbles during solidification. The ultimate intervention is vacuum die casting. By utilizing a vacuum valve to actively evacuate the atmosphere from the steel die moments before injection, foundries physically remove the air that causes trapped gas porosity. Theoretical metallurgical design must be strictly enforced by physical interventions during the millisecond window of injection. When we pull back to view high-stress automotive components, like complex engine blocks and transmission housings, the scale of the engineering becomes clear. These parts survive extreme real-world conditions due to a strict architectural balance: alpha aluminum providing ductility, refined eutectic silicon ensuring wear resistance, and copper and magnesium acting as strength multipliers. Their operational lifespan relies on the successful suppression of destructive beta iron plates and the elimination of interconnected shrinkage porosity. An engineer inspecting a failed casting reads the thermal, chemical, and pressure history frozen into the metal. High-pressure die casting is the precise engineering of microscopic phase dynamics to guarantee macroscopic survival.